It's another lovely day, and welcome back. And as usual, thank you very much for watching this lecture video. In this lecture video, we're going to go through benzene molecule. I'm going to start the lecture with a short history about how did we get the structure of a benzene molecule. Benzene molecule was actually found in three different events sometime in the mid of the 19th century. And as you see, in like 1822, 33, and the last one was 1845. And about the benzene molecule, after actually they developed some element analysis method, they figured the benzene molecule has 6 carbons and 6 hydrogens. And after that one, they started, to come with some geometries for such a molecule. As you see, from A to F, we got all those possible structures. And German scientist with the name of Kekule, he came with one, like technically the best proposed structures for benzene molecule, and from that time we adopted the structure, and the structure is something between technically F and E, or E and F structure. And I'm going to go through them now. So he said he said the benzene molecule is made of technically two molecules. We have an equilibrium between those two molecules. The only difference between those two molecules is position of the double bond. And for instance, the double bond is here. And next time we're going to move the double bond, and the double bond now is going to move there, and now it's going to show up there. So we have equilibrium between two identical molecules. That the only difference between them, based on his, hypothesis, was like position of the double bond. Later, when they developed the resonance structures and all, like also we came with the valence share electron pair repulsion theory. We said they said, like, you know what? We are dealing with a hybrid of those. And what do I mean by a hybrid? I'm talking about like a double bond, instead of, technically just being fixed in one position all the time. It can change its position. And this one, it keep happening. And the molecule that we see is a mixture of, all those cases, okay? And so whenever we are trying to run a chemical reaction or whatever, and we're going to be dealing with a mixture of those, structures, okay? Mixture of those structures. And instead of, showing the triple bond and, double bond in different position, chemist has tendency to draw a cyclohexane and then put one technically just a circle inside of the, inside of the molecule to show that we have a double bond. We have 3 double bonds and keep changing their position. Okay, now let's go a bit in depth about the benzene molecule. And as you see, benzene molecule technically is a cyclohexane molecule that it has 3 double bonds. And it's going to create 2 rings. One ring, it has, like you can say it, and it has a positive, technically sign. When I say positive sign, I'm talking about this lobe here is positive. And if you connect all those positive to each other, you will get one ring. And there's another ring that we can get it through connecting the negative lobes to each other. And that's going to give you another, ring, and it will be at the bottom of the molecule. So we have 2 rings, one up, one down. And those 2 rings, the only difference between them is their phase. Okay. Now let's go a bit in depth about the benzene molecule. Benzene molecule is made of carbon and carbon hydrogen atom. And we show it by such a ring, an hexagonal, that it has 3 double bonds. Carbon, it has 1s2, 2s2, 2p2 hybridization, the electron configuration. And last orbital is a p orbital that it has only 2 electrons. So px, py, and last orbital it will be pz, which is empty. Now, in order to connect carbon to 3 atoms, you need to have at least 3 singly occupied orbitals. Okay, but right now we have only 2. And remember that the s orbital, the 2s orbital, is already occupied and is full. Now, how carbon can make 3 bonds? Carbon is going to go through a hybridization. It will take 1 orbital from S and 2 orbitals from P, and it will give us 3 hybrid orbitals. So we get 3 hybrid orbitals, and we use 1 from S and 2 from P. So the hybridization, it will be sp2. Okay, let's show carbon. This is carbon, and it's going to have 3 hybrid orbitals, 1, 2, and that's going to be the 3rd orbital. Okay. Again, we have 2 plus 2. We have 4 valence electrons. Let's show those 4 valence electrons. Carbon is going to put 1 electron inside each of this hybrid orbital. So then it can make 3 bonds. And it's going to use one of them to interact with hydrogen. So hydrogen is going to reach the carbon with opposite spin, and that's going to give us 1 sigma. And then the carbon neighbor atoms. Okay, so we do have some carbons. So this is another carbon, that's another carbon. Those carbons, they will come with 1 opposite spin, and they will give us sigma. So right now we use 3 electrons at a 4, and we made 3 sigma bonds. Let's show the 3 sigma bonds. Okay, so for instance, this is the atom. Forgive me. This is the atom that we are talking about. Right now we said we made the 3 sigma bond, 1 sigma, 2 sigma, and that's going to be the 3rd sigma bond. Okay, now what should I call this bond? We call it pi bond. Okay, and how do we get that pi bond? If you look to carbon, out of the 3 p orbitals, we use only 2 p orbitals. Okay, and we have 4 electrons, and we use only 3 of them. So that means we are left with 1 electron, p orbital with 1 electron. We are left with 1 p orbital that it has 1 electron. Okay, so I have another p orbital. Where's that p orbital? Okay, that p orbital is sitting on carbon. Okay, so that's a p orbital that it has only 1 electron in it. And carbon, it can use that 1 electron and do interaction with neighbor. Okay, so that p orbital, okay, that you can find it in any carbon atom, it will be used to make a pi bond. I'm going to show them, for example, here. Let's show it on this carbon atom. Okay, so on each carbon atom, we have a pi orbital. And that pi orbital, it has 1 electron in it. Okay, so 1 electron there, 1 here is down, and they're going to have interaction. Okay, this one, let's call it, for example, that's a positive lobe. That one is the negative lobe. So this one is negative. Again, they will have interaction, positive by positive, negative by negative, and that's going to give me pi bond. Okay, so the fourth interaction of carbon will be made by running a pi bond, and the pi bond through a parallel interaction. Okay, so now we have a pi bond, and we have 3 pi bonds. Okay, and as we said, the hybridization is sp2, and we have a pi bond because hybridization is sp2. The bond angle, expected bond angle, it will be 120. Okay, and expect the same thing. For example, here I expect it to be 120. And now, what's the hybridization of each carbon? Each carbon, we said sp2, and that hybridization is going to interact with hydrogen atom to make a sigma bond. As hydrogen atom, it comes with s orbital. Before I go through, what's the difference between benzene molecule and molecules like that they have double bonds, or let's say triple bonds, 3 tri bonds, and so I want to show you what's the difference between those two. And imagine you have a molecule that is A is turning to C, and the activation there's activation energy for it, and also we do have delta H for it is -30. In the second reaction, we have a B molecule is turning to C, so it's the same product. Okay, so now we are talking about same product, and the delta H for the second reaction is -45. So C is the product, okay, and reactant, it can be A or B. Okay, choose one of this reaction. It doesn't matter which one. And so start with the first, for example, the reactant, either first or the second one. It doesn't matter really which one, and just simply call it A or B. A or B. Imagine I decided to go with this, for example, I decided to go with the first one, and I'm going to call this one A. So A is turning to C. The gap between A and C, we call it the delta H. So I'm going to show the delta H. This is the gap between them. Delta H for this reaction is equal to minus, we said, 30 kilocalorie per mole. Okay. Now, where do you put B? Higher than A or lower than A? Look to this number, the delta H. Delta H is bigger than the first reaction. So that means the gap between the reactant and product must be higher than the one that we have. So I'm gonna put B somewhere, for example, here. So let's say we're gonna put B somewhere here, and this is gonna be B. Again, B is gonna go through a transition state, and it can be completely different methods, and it will give us this product. Let me show it with a different color. Hope I can get it right. Okay, so imagine we got this one. Okay, now the barrier between B and C, sorry, the gap between B and C, that's going to be the delta H. So this is going to be the delta H of the reaction, and is equal to minus 45 kilojoule. Okay, which one of this reaction is generating more heat? Clearly the second reaction. Okay, so the second reaction is creating more heat than the first one. What does it mean? It means B is less stable than A. Okay, listen carefully to this one. B is less stable than A. Why? Because when I turn both to C, I got less heat from A. Less heat from A. So that means A was more stable and B was less stable. And because B was in higher level of energy, gave me more, okay, more heat. So I got more heat, and the sign for it is the delta H. Okay, so now that we know this one, we're going to go after benzene molecule and we'll compare it with hexane, the hexene molecule. Okay, so imagine you have 3 moles. Okay, 3 moles from hexene molecule. Why 3 moles? Because the benzene molecule, it has 3 bonds. So I'm going to say, okay, instead of using benzene molecule, I will use hexene and 3 moles from it, and I will treat it with 3 moles of hydrogen gas, and that's going to give me 3 moles from cyclohexane. Okay, I repeat this one with the benzene molecule. I add hydrogen to it, and it will give me cyclohexane. Okay, so I repeat this one. So I go 3 moles from cyclohexane plus 3 moles from hydrogen gas. That's going to give me 3 moles from cyclohexane. The delta H of the reaction is minus 86.7. Now, when I repeat this experiment with benzene, and benzene, it has 3 double bonds. Because it has 3 double bonds, in order to saturate them, I need to have 3 moles from hydrogen gas, and that's going to give me 1 cyclohexane molecule. Okay, and theoretically, you expect them to be maybe the same at least, okay? Because benzene, it has 3 double bonds. Cyclohexane, it has only 1, but we use 3 moles from it, so I expect the energy to be the same, okay? Energy is not the same, okay? Clearly, it's not the same. And also, we see this in the hydrogenation of benzene give us less energy. What does it mean? It means benzene is more stable. Benzene is more stable, or benzene, it has something that is making it stable. And what's the gap between them? The gap between them is hanging around 36 kilocalorie per mole. So something is making benzene is more stable, and that's the reason we get less heat. Okay, the first one we got 87 almost. This one we got almost 50. So the gap, as I said, is around 36 kilocalorie per mole. Something hidden that is making benzene more stable, and that's one we call it resonance energy. So the resonance energy is the reason that benzene is creating less heat. And next lecture, I'm going to go through this one. But for now, let's stop here, and thank you very much.